So, thank you for attending. My presentation today is about the camera and video architecture that I'm researching, and it involves PipeWire and also libcamera, which I will be talking about in a minute. Who am I? I'm George. I'm principal multimedia engineer at Collabora. I work mostly on things around GStreamer and PipeWire, and I'm also the maintainer of WirePlumber, which is like now the default PipeWire session manager in the desktop and in embedded projects in AGL as well. Let's talk about cameras to start with. So you all know what cameras are. Fascinating devices. They capture some light, they take it through a lens, they channel that light to a sensor, and that sensor turns the light into electrical signals. And then that has to be converted to some digital format, be processed, because the light that comes in the lens is not actually what we see in the picture when we take a photo. There needs to be some processing in between. And after that, there's probably some compression before we get the signal to the CPU. Now, that's a simple camera. Many, many years ago, that was the entire pipeline. Nowadays, we have more complex cameras. Like in our phones, we will see the back of the phone has like 3, 4, 5 cameras, 5 different sensors. They're not actually different cameras, but different sensors of the same camera. So they have different properties and they capture light differently. And that needs to be converted individually to individual images that then need to be processed together in order to create a final image or image stream. And depending on the use case that we are capturing for, there may be different steps involved, different algorithms, different sort of processing, different sensors being enabled, or combinations of sensors. And apart from the use case, other things could make that change, like the zoom level might change which sensor is capturing, for example, and so on. So what we need from the user space is basically an API that will allow us to program this entire pipeline with all these complex sensors and complex signal processors that are available, tune all of that so that we get some output stream for a specific use case. Like in a mobile phone, for example, we would have these 3 use cases that I have on the slide. Like you might want to take a still picture, high resolution. You might want to take a high resolution video stream. You might also want to take a video stream that is low resolution for the purpose of showing it to the screen so that you can preview what you're going to take. The common thing around all these complex cameras nowadays is that they have high computational requirements. Either that might be for correcting and combining images from these different sensors, or it could be other things like analyzing, detecting things, like for machine vision applications. And there are a couple of processors involved in that. There is the integrated signal processors in the camera device itself. Sometimes there is an MCU in the camera. Sometimes the host CPU is involved as well and doing parts of the processing. There's a blurry boundary in between those, and different cameras and different implementations of cameras require different setup. Nowadays, I mean, I haven't researched much, but I suppose we need to have some integration also with processors that are specific for machine vision, machine learning applications. And all of that basically leads to images going back and forth, different blocks, and these blocks might be anywhere in that pool of resources. So we need something that can manage this, can make a pipeline or that programs all these different sensors, ISPs, CPUs, whatever, to generate a final output. And that software is libcamera. So libcamera is a library that provides an API and that is able to manage all of that, all the different sensors, the ISPs, and everything. Because from the Linux kernel, what we get when we enable such a device is we get lots of different video for Linux devices, and each of those might be a sensor, might be an ISP. So you need something to orchestrate that, and that's what libcamera does. And it has the ability to run also device agnostic code. So the vendor of the camera can push device-specific configuration or code that will orchestrate that for that specific camera or for a specific use case. It also has the ability to run algorithms, which, if they are, sometimes they are proprietary, and that is something that camera vendors also sometimes want to keep proprietary. And because it might be proprietary, it doesn't have to be, but it might be proprietary, so there is a system that can run all these algorithms in a sandboxed way to protect the rest of the system from potentially dangerous code. And all of that comes to user space using an abstract C++ API. Nicely done. Now, libcamera solves one part of the problem. Like, it manages to orchestrate a single camera with all of its complexity. How do we move to an even more complex setup where instead of having one camera, we have multiple cameras? How do we combine data from separate devices, entirely separate devices? And also another thing is, if we have separate devices and separate inputs, how can we, let's say, process things in different processes and potentially in different containers to orchestrate the processing in a way that it's not a monolithic application? Because as complexity increases, we need to have this separation of responsibility for different tasks. Ideally, we should have different processes so that we can also replace some of these parts later on to go to a different system to do something else without having to rewrite the entire processing application. And to solve that problem, we have PipeWire. So PipeWire, you must have heard of PipeWire before, being an audio server. It's not just an audio server, it is basically a multimedia bus. It's something that enables applications to create multimedia graphs that go from process to process and share resources, media resources. It is able to do that low latency and zero copy as well, so data getting out of a process and getting into another process doesn't have to be copied, and it goes out really fast. And it has the additional feature that all the management of that pipeline happens by an external component, which is WirePlumber, which is configurable, scriptable, so we can change the entire pipeline to do exactly what we want per use case. In a picture, PipeWire looks like this. So we have the PipeWire bus, basically here, where all the applications and all the cameras and all the outputs, etc., connect. So, for example, PipeWire has integration with libcamera, so it can expose the libcamera devices right here as input nodes, and this become available just for any application to capture. It doesn't have to be limited to hardware cameras. It could be also some input that comes from a process. So for example, you could have a process that receives a camera stream from the network and feeds it to PipeWire, and it presents itself just as another camera. For what applications are concerned, this is just another input node, just like those two. So it provides also the versatility of like being able to change the backend really easily and combine different backends as well. And then you can have like other processing nodes which are provided by applications or by hardware. Here I have the example of a hardware encoder. Also hardware decoder would be possible. This is something that is actually not there as a functionality. PipeWire doesn't integrate with hardware encoders and decoders yet. But it's something that I'm actively researching on how to do. I think that would be very useful. And yeah, maybe then other applications which are basically consuming the data streams. So here I have an example application which is a display application that potentially needs to have multiple inputs from different cameras and displays them somehow combined. And I have the example of another application which is a recorder that also takes input, processed input from these processing nodes and then records the output. So you see how you can have different like blocks combined together with this multimedia bus. And something else that is also shown here is that the applications can be containerized. It's not necessary, but it's a possibility. So you can have the applications running in different containers, and if they are in different containers, then you also have like restricted connections. So every application will be able to connect to the resources that it's allowed to connect and not to anything else. That gives you some sort of security to the system. So a malicious application that somehow ended up being the recorder application, for example, it cannot consume directly output from, let's say, these cameras, because maybe we have a policy that restricts it to consuming output from these nodes, and then it won't be able to do anything else. Now, why I think this is important, especially in automotive, there are so many different systems that make use of cameras nowadays, and it's increasingly popular, and I think it's also getting to a point where it's pretty complex. We have different cameras around the car, and we need to combine all this information somehow to give final output to the user. And of course, I'm pretty sure that this can be done with some specialized hardware. For example, say you want to do a 360 view of your car, which is already deployed in many cars out there. You could do it like with a complex hardware, specialized hardware that does this job. But that doesn't scale very well. It's something that you have now, it works. Maybe you want to change something in the future, you will have to redesign the hardware, and as soon as you go redesign, you find that you need a new chip. That new chip changes the whole design, and you're basically back to zero. While with software, it scales better, because especially if you have a system that to orchestrate all of that, you can have small chunks of processing around your software stack and combine them appropriately for each use case and for each iteration of your of the development. And I think that scales better. Other applications that can use this Some interesting example that I've thought of is cloud processing as well. So imagine that you have a server that needs to process a lot of user-generated content that comes from the network. So your cameras send data to a cloud service, or it may not be cameras, maybe something else. And this service needs to process that. And while you could build monolithic applications that do the entire processing, you could also split it out and have separate containers on your server that share the data through PipeWire to create a pipeline, processing pipeline with different containers involved. Mobile multimedia, obviously, I mean, this is something that is interesting to the mobile stack, and of course many other applications. Now, I have prepared a demo to show this PipeWire node process splitting pipelining. And this demo is going to involve libcamera, but it's not going to show off libcamera, basically, because I'm running this on a laptop, actually on a virtual machine here, that doesn't have any complex camera. It's a very simple UVC camera that's getting exposed to the virtual machine. So I'm not showing off libcamera, I'm showing off PipeWire and the capabilities of that. And to show that off, I have written some scripts, shell scripts. I'm going to start with the face detect. So I have written a script that takes input. First, let me say that all of these scripts are starting processes based on GStreamer. They use GST launch, which is the main GStreamer launching tool that can launch arbitrary pipelines. So all of these scripts basically launch a GStreamer process. The face detect one, it takes input from PipeWire. It doesn't have a specific source, so WirePlumber is going to hook it up to the camera by default. And then it takes that through the face detect element, which uses OpenCV to detect a face. And then it takes that out again to PipeWire. So when I run this, I'm going to see absolutely no output. But I see something is playing there, something is running, and my camera is open here. So the next thing that I have is the face detect output, which basically takes input from PipeWire and displays that to a window. So I'm going to run this. And there it is. So it detects my face. And because I'm using the PipeWire mechanism, I can now take the same output from the face detect script and display it also in another window. I can have multiple of those. And they show the same output because it's the same thing that comes out of the face detect script, the first script that I launched. That is also visually shown in like the graph. This is a tool to inspect the graph of PipeWire. So I have input coming from a camera going into face detect, and face detect out goes to the two output processes that I have launched. Now, I'm opening a camera here, but I could be doing the same thing with a video file, right? I could simulate that. It doesn't have to be a real camera. So for that purpose, I have written this video source, which basically plays a file and outputs the video to PipeWire. Video source. And again, that doesn't have any window. It outputs the video to PipeWire. So it's now a node that is available for consumers to take If you look at the graph, here I have video source. It's not connected anywhere. And then I have another script that is video output that, again, it's like face detect output. It takes the input and displays it on a window. So I have this output window here, and I could launch also another. Oh, no face detect. Video output. And something happened. I think it crashed. Oh no, that doesn't look good. It doesn't look good at all. Yep, I think the virtual machine just crashed. Sorry about that. But yeah, the idea is that you basically have all these different, I'm going to reboot it. I think it's like reset. Yes. Anyway. This is the idea that you can have different processes that do processing, and another thing that I had also in the demo is you could have a process that also combines. So I had one more script that basically combines the camera and the video source and shows them combined in a single window. So that shows how you can do also mixing. You could take like a bunch of cameras and mix them together in a single application through PipeWire. Yeah, that virtual machine is really, really unhappy. Anyway, I didn't have anything else to say. So, any questions?
So everything you demoed, is that current release runtime packages?
Everything I demoed is upstream versions of PipeWire and WirePlumber running on Debian 12, the latest Debian testing release. So yeah, you can do it with upstream components. No need to patch anything. Just write a GStreamer script. Take input, take output. And if you don't want to use GStreamer, there is also examples in the PipeWire source tree. If you look at under source examples, there is video input and video output examples as well. It shows you how to directly use how to directly use the PipeWire API.
And then the reason why you have two separate windows, you just want to illustrate two processes running different parts of the graph?
Yeah, essentially, what I wanted to show is that you can have the same input going to different parts of the graph, so splitting off to different processes. And the other part, which I didn't manage to show, is the vice versa. So you can take two inputs or more and combine them in a single input node that mixes the inputs.
So would you consider that our architecture to have independent processes for a complex graph?
Yeah, that's exactly my point, yeah. So I think it's better architecture to have independent processes that do only one part of the whole processing, because that essentially allows you to reuse those in different scenarios instead of having to do a monolithic application. Traditionally, this is how it works. Like you build a usually GStreamer-based, but it could be something else, GStreamer-based application that has to manage the entire multimedia graph, because traditionally only one process is allowed to open the cameras, right? So it will open the cameras, and then it's totally in control of those cameras. And it's the only application that can take input and combine it and do something useful. But if you have PipeWire, then you can take these inputs, channel them to different processing software, which could be completely independent, and do more with one system. So you could be like showing a camera to the display and recording at the same time with two independent applications, instead of having to build that into the same thing.
And then in terms of zero copy, how does that PipeWire is managing the buffers in a common location, or is that implicit that it's zero copy? Or?
So zero copy is achieved by sharing buffers with either memfd or DMA buff. So PipeWire will pre-allocate, traditionally in the software processing, PipeWire will pre-allocate some memfds that are basically shared memory buffers, and then it will write into those and give them off to applications. And that's how data is exchanged between two processes. Now, if you put some hardware in the mix, and let's say you're capturing from the camera directly, then you can do a DMA buff transfer directly through PipeWire to the application. So the application gets a DMA buff that actually came from the camera directly. And same thing is with hardware encoders, decoders, when we have that available. The idea is to be able to get DMA buff directly to the application. No, DMA buff is part of the Linux kernel. It's a Linux kernel API that allows you to access a buffer that resides in a hardware resource. So the video for Linux API, for example, when you capture something from a camera or from a capture device, it might not be a camera, you can ask the API to give you a DMA buff. And what it does is it gives you a file descriptor that refers to the hardware memory. And depending on how the memory is configured, you may be able to mmap it on the CPU. You may also not be able to mmap it. So it may be a hardware resource only. It may be something that only the hardware can process. But thing is, you get a handle to the user space that's managed by the kernel, and you can pass it around to different components and do something useful. Yeah.
When you said like upstream, I assume you mean, realistically speaking, like latest versions of PipeWire are converted?
Latest, yes. Although it doesn't have to be latest. It could be like maybe a year old as well would be fine, because we haven't changed anything recently. I gave the same demo 6 months ago at the ELC conference in Dublin, and I was using the versions at the time, and it was the same demo, nothing changed. In AGL, I'm not entirely sure because the versions are a little bit older, but I think it should also work in AGL.
It's on my to-do list.
Yeah, in any case, it's... Yeah. In any case, my colleague Ashok is working on the updates of the recipes. So we will soon have updated recipes to try. And my intention is, when it comes to AGL, my intention would be to enable these things, enable the video processing in PipeWire, and also maybe integrate libcamera, because this is all low-hanging fruit. It's all available there. And I mean, we could have it and experiment with it.
What's your usual test platform for like libcamera integration?
Libcamera, okay, so personally, I haven't tried much of libcamera in in other devices. I have played a little bit with Raspberry Pi and a Raspberry Pi camera sensor, and I just got also a RockPi, which also with a RockPi, Raspberry Pi sensor, but RockPi device that is able to show that off. It's still not a very complex camera, it's one sensor, but it's closer to what libcamera is for. Libcamera can also do UVC cameras, USB cameras, but that's not the intended target device, and it doesn't have any advantage to direct video for Linux in that case.
Yeah, that's the thing that I've been thinking about. If we want to demo camera stuff, is some of the boards that we would likely want to use don't necessarily have a camera input that's reflective of the product. So it's more interesting if we want to actually do a product looking demo. So, thank you.
Yeah. Would be interesting to research cameras and see what we can get in AGL. Yeah.
So in terms of scene stitching between two images of PipeWire, what would be your approach for that?
So for stitching, I would do a separate process that takes input from the 2, 3, 4 cameras, how many they are. and then apply some algorithm that combines them. I would probably demo that with an OpenGL application that just combines these different images from different cameras.
So it's effectively an copy into the GPU.
Yeah, that's how I would approach it. I mean, there may be different, more appropriate, efficient ways, I don't know, but that's probably what I would do. And it might also be the case that some hardware has the ability to directly input DMA buff to the GPU. So you could get a texture out of a DMA buff without copying the pixels into the CPU. So that would be the ideal. If the hardware can support it, it will be the ideal scenario of taking the inputs from the cameras through DMA buff, channel it to the GPU directly, let the hardware copy these into the GPU, and then apply some OpenGL transformation to make that happen.
Okay. And are your scripts available, or are they on GitHub?
I haven't uploaded them somewhere, but I can do that afterwards. That's
Yeah, I'd love to reproduce that.
yeah. I will do that right afterwards. Any other question? Okay, thank you very much.